How are you guys? Welcome back to my YouTube channel. Today we'll be dealing with steam generation. This is part 1 and 6 power machines, right? So I'd advise you, if it's your first time watching my video, or if it's your first time we have not subscribed to my YouTube channel, may you kindly subscribe to my YouTube channel and click the notification bell so that you'll be notified whenever I post a new video, right? So I'll give an example 1 here. It says the information below applies to a steam boiler plant. All right, take a note. I did the question for, I did the introduction for steam plants, all right. I advise you to watch the previous video if you're interested to know some more gymnastics. I've introduced this. All right, so here we have the average pressure of steam, which is 1.5 megapascal, right? We have this, and you see all this is what we are given. I want us to do this. Here is the question. It says use only the steam table to answer the following. Calculate the mass of steam generated. Okay, in kg per, check this, in kg of fuel. All right, want us to check something here. We've discussed this is a data. We have this here. We've discussed about these things here. The first part will have the economizer. Then the second part will have what we call evaporator. The second part will have what we call the superheater. All right. Then remember, here we have H1. Here we'll have H2, H3, and H4. All right. From this data, 1.5 megapascal, the average pressure of the steam 1.5 megapascal. The average pressure is taking place here is for the superheated. That is the pressure of the H. It is the superheated steam. It's a superheated pressure. That one, yeah, it's a superheated pressure. Here will be at P4. Here will be the P4. The pressure there, which is the same as 1000 kilopascal, 1500 kilopascal. Remember, here we have P3, or remember the pressure here and there is the same, so P3 is equals to P4. Right, that means pressure here, since we know that the pressure here at P3, I can say P3, maybe example there will be equal to 1500 kilopascal also. And this is what we know. Remember, those are superheated one. Then we have the final steam temperature of 350. It's here. Final, it's at the end of yours. It's here. Here we have our temperature also there. This is from here. This is a tea soup. This one, we have our temperature there, which is 350 degrees Celsius. All right, for that portion. All right. Then we have water again. The temperature of the feed water, inlet temperature is 44.8 degrees. To check that it's a feed water. Feed water is taking place here. Remember, the feed water is taking place there, isn't it? So our temperature here, I can say T in the inlet temperature there is 0, is 44.8 degrees Celsius. All right. We've given the mass of combustible, the chimney temperature. Okay, all of this now, as you can see. All right, this is what we have, guys. I can see here, I can write chimney. What do we have for chimney? We have there the mass, the heat. Okay, chimney. Base, we have the temperature there. The chimney base, that the chimney page, which is T. What that one is TF. Chimney page TFG. Okay, TFG. The mass of the gas there, or the chimney page of the temperature. Also we have, okay, the mass of the combustible in fuel, the mass of the combustible, mass of the combustible. All right, we have the mass of the combustible that we'll discuss also. Okay, the chimney base, we have this temperature. Chimney base, the chimney base, which is TA, is 100 degrees Celsius. Remember, those is for chimney. All right, then that is what we have. Or it's a pressure, that one. It's 100. Or pressure. PA must be pressure the chimney base, or pressure the chimney base can be PA. It's equal to 100 kilopascal here. This is what we have. We have here the boiler temperature is 20. The temperature in the boiler room is 20. We must know this take place at the chimney also. This will be TA, is 20 degrees Celsius at the boiler. The temperature at the base of the chimney. Then we have fuel capacity, we have specific heat cap. Okay, here this is the mass of the combustible. We have the mass of the combustible there. We also have the mass of the combustible. The mass of the combustible there. The mass of the combustible flue. This is MC. The mass of the combustible is 0.94 kg per kg fuel. Then what do we have again? Stroke from our data. Caloric value there, 32 megapascal. That is CV. Caloric value 32 megajoules per kg. Thermal efficiency of the plant, of the whole plant. We have the thermal efficiency. You can see plant of the whole plant. It's equals to 70 watt, 74 degrees. Right, then the heat loss superheated to the superheated in flue gases. That the heat loss in flue gases heat loss in the flue gases, heat loss to the steam in flue gases, heat loss to the dry product is that we've given. Then we have the specific heat capacity of dry flue, the heat capacity of water, heat loss to the superheated steam in flue. That must be, guys, in superheated in flue. What is superheated? Steam. That's the in flue gases. Must be of the moisture there. Talking about the heat of the moisture there, guys. That must be the moisture. We have this must be of the moisture. You can say M. This is the moisture. So 144.5 kilojoules per kg of fuel. All right. We've given the specific graph. We've given also the heat lost by dry gases. GDG, dry gases, is 6 megajoules per kg of fuel. Then we have specific heat capacity of water. We have given there to be 4.2 kilojoules per kg, kg per Kelvin. We have given also the specific capacity of what? Of the gas, which is 1,046 kilojoules per kg per Kelvin. This is what we have. This is our data so far. All right, let's check question. What does it say? Using the steam table, answer the following question. Number 1, calculate the mass of the steam generated in kg per kg of fuel per kg per kg of fuel per. Check that part, meaning that in kg per guys, kg of fuel. That means here the mass of the fuel, we take it as 1. Must be, if you find that must be S, we'll take that as 1. Okay, number 1, we have to do our thing. We want the mass of the steam in per kg of fuel. All right. What can we have? That we have the efficiency of the plant. We can get it here from the efficiency. We know that the efficiency of the plant is equals to mass of steam into H4 minus H1, right? Divide this by mass of fuel multiplied by CV. All right. This is per fuel, right? This equation would be like this: H4 minus H1 over 1 times CV, like this. Remember that now, because per means 1 per kg of fuel. This must be per kg of fuel. We replace the mass of fuel with 1 per kg of fuel. So this is the equation that will use the efficiency of the plant. All right. Remember, H4 is the same as the H superheated. H1 is the same as HF. We know that. All right. We're supposed to find H superheated enthalpy in there using a steam table, and HF using our steam table. So let's find that. Let's check H4 at what? At the pressure of 1,500 and temperature of 250. Here we'll check at the temperature of what? Of 444.8 degrees Celsius. Let us check those just that we will those enthalpies that we can get, which those let's check those enthalpies, right, that we will get from our steam table. From our steam table, here is our from steam table. Let's check. We want the temperature 44.8, 44.8 temperature. Remember here this is for temperature, isn't it? So let's check 44.8. 44.8, here it is in this row. So what do we want? We want HF. Here it's HF in the row of in this row going downwards there. Let us check what is that in this row. This will correspond, it goes like this. It's here it's 100 and what? 188 we have there. As you can see, this is what is HF. There is 188. Fine, we have that. And also we're supposed to go to the superheated using the temperature of 350 and the pressure of 150. Let's check now our superheated steam. Okay, it's our superheated the temperature. Here we have a pressure on the top there. We have the pressure and the temperature. This is temperature and pressure. We want 350 and the pressure of 1500. All right. Let's go. Remember, this is the pressure going down. This row represents temperature. This row is for what? Pressure. Let's go. Here we have 350. Supposed to go down there until I reach the pressure of 150. 1500. Let's check. Oh, here it's 1500. As you can see, our H soup here it is 1500. There you go. Where they meet here. So that is the enthalpy 3148. 3148. 3148. So we have this. We have our values. As you have seen there, guys. So the enthalpies, the H4 we found that to be, remember this is H soup and H4 is the same as H soup. Superheated enthalpies, we got that with 3148. Remember it's in kilojoules per kg. Then H1 whereby is same as HF, we found that this to be 188 kilojoules per kg. So we can substitute our efficiency. It is 74 there. You'll say 0.7 is 74%. The mass of the steam, we're looking for the mass of the steam multiplied by H4. Here it's our H4 is 3148 minus 188. Divide this by the caloric value. Remember must be in kilojoules. They've given you in mega, they say 32 megajoules. You're supposed to do this, must be in kilojoules. So substitute it, supposed to substitute it as a kilojoules. This will be 32 times 10 to the power of 3 kilojoules. Must write this as a kilojoule so you understand. Then this will be 32 times 10 to the power of 3. So we're supposed to have, to make this the subject, the mass of the steam, the subject of the formula, multiply there, maths there, apply the maths, you multiply there, alright, then you divide by that. Mass of the steam will be equals to 0.74 multiplied by 32 times 10 to the power of 3 divided by 3148 minus 188. So what do we have here? This will be, if you punch that, will be 8 kg per, remember, per kg of fuel, per kg of fuel. Or you can represent like this, kg of fuel, and write f, little f there down. That means the kg of fuel is up to you. So that is what we have now. The mass, we got the mass of what? Of the steam generated per kg of fuel. Alright, number 2 says calculate the equivalent evaporation from and at, we have discussed about this, at 100 degrees Celsius. I've discussed about this evaporation, equivalent evaporation. Number 2, we've discussed about equivalent, supposed to calculate equivalent evaporation. We know equivalent evaporation would be the mass of steam over H4 minus H1 over mass of fluid multiplied by specific of diarrhea. Sometimes this can be given, will be written EE. Most of the time this is denoted by EE, equivalent is denoted by EE. You can write like this if you want. Again, H4 is the same as H superheated, then H1 is same as HF, mass of full multiplied by caloric value. So one in the same thing. Then we substitute what we know. Right. The mass of steam is 8. We have calculated it previously. The mass of the steam is 8. Alright. H4 is what? Is 318,348. H1 it was 188. All over the mass of fuel we took it as 1. Right. We take that as 1 multiplied by the caloric value, which is 32 times 10 to the power of 6. Then what would be our equivalent? If we punch this on our nicely calculator, equivalent there will be 10,49 kg per kg of what? Of fuel. So that we are done with question 2. Question 3 says calculate the mass of the moisture in flue gases per kg of fuel, Alright. Number 3. I've discussed about about the moisture. For moisture, I've discussed about the moisture, guys. The formula for moisture, if you've watched my previous video, remember we've discussed about the most important formula there for moisture. Remember, I have laid some, we've talked about the moisture. I said if you are given the heat of the moisture, this will be the mass of the moisture, right? Into multiplied by superheated enthalpy minus by the specific enthalpy of the minus by specific enthalpy of water, and then multiply this by what is this into temperature of the boiler at the boiler temperature, like this, at the boiler temperature. We've discussed about this, the mass of them, the mass of the moisture. We've given, obviously, while I'm using the heat, we've given the heat of the moisture here. The heat of the moisture is there on our data. On our data, we've just grabbed it, 1445.5 kilojoules. We have that. All right, substitute what we have. All right, we have 1445.5. We want the mass of the moisture. This is the mass of the moisture. HS superheated, right there, here, superheated, and with this temperature is the difference temperature, right? That will be given, that will apply there. Remember, this will be we'll be checking at remember, HS of the moisture would be taking this from the our, what is that, we've given the pressure of this, where was that pressure of at the boiler, where at atmosphere. You must know when you're talking about moisture at atmosphere, PA, this one, it was 100 at this, at that pressure, plus this temperature, the chimney base is 250. We have this at the chimney base is 250. Remember, now at moisture we'll be talking about, we're focusing at the chimney is there. So steam table will go there to pressure of 150, or we go to the temperature 250 there. So let's see what is our superheated. Remember, this will be, we'll use our superheated. We're supposed to find H soup, right? You have to find the H superheated here. Remember, this is a superheated. We have to find the superheated steam, right? So let's go there and find the superheated using those values that I've shown you, 250 and 100 Pascal, 100 kilopascal from the superheated steam. It's our super heated steam. 100 kilopascal and 250. Temperature here is 250. Our temperature is here 250. Let's check the pressure. 100. Where is 100? Here is 100. Our temperature here is 100. It's 100 and we are looking at 250. Temperature of 250. Then here is the pressure going downwards. We'll go like this until we reach the pressure of 100. Here is the pressure of 100. Here we have H soup. Where the line meets will be with that one. Okay, this line will meet here. That means will be that enthalpy there. Here's our enthalpy 2976. We found that. As you can see, this is how you evaluate this thing, guys. So H soup, as you have seen there, it was 297.5. Then we minus the enthalpy of water were given. Specific enthalpy of water 4.02 multiplied by 4.2. Then the temperature at the atmosphere at the boiler, this is a boiler basement. At the boiler base is 2080. It's at the boiler base. Multiply this by 20 like that. Then the mass of the moisture will be 1444.5 that divided by 2975 minus 4.2 multiplied by 20. All right, then we'll have the mass of the moisture. The mass of the moisture will be 0.5. If I punch that, kg per kg of fuel. All right, this we have now the mass of the moisture. Then number 4 says calculate the mass of air per kg of fuel. The mass of air. All right, number 4, the mass of air. The mass of air. All right, remember that there's this nice formula that says the mass of air plus the mass of fuel must be equal to the mass of the moisture plus the mass of what is this the mass of the this is the moisture, fuel, mass of gas, like this. So we want the mass of what? Of air. The mass of air, you make that the subject. If you make that the subject, guys, this will be the mass of the moisture plus the mass of gas minus the mass of the fuel. So we have to get the mass of the gas. The mass of the gas, I've talked about this information. We're given the heat of the dry gas, which will be the mass of the gas there, multiplied by specific capacity of the gas, right? Then here we'll have change F of the gas minus TA. Remember, you were discussing about the gas. So this, it was what the dry gas is. From here, as you can see, guys, we've given I want you to shake them the heat loss due to dry products is 6 of that 600. Heat loss due to dry products, there we'll find our gas there, 6,600 megajoules. We have the dry products 600 megajoules. This will be times 10 to the power of 3. Make it, not 100, times 10 to the power of 3. Remember, must be in kilojoules. So will be just like that. It's equals to this mass of the gas that we want multiplied by specific capacity, that it was 1,046 into the temperature. This is 250, guys, minus 20 here. As you can see, 250, that will be final, the initial one of them at the base. Then the base, or the specific capacity it is of the gas. So this is what we have. Then we make the mass of the gas, the subject, would be 6 times 10 to the power of 3 divided by 1.046 times 10, 150 minus 20. So therefore mg will be mass of this gas, be 24.9 kilojoules, kg, the mass is kg per kg of fuel, remember. Alright, so this is what we have. Now we want the mass of the air. We use what we have talked about, this there. We'll use this to find the mass. What's wrong with this? I want to grab this. Alright, so the mass of air, the mass of the moisture, we have calculated the mass of the moisture previously. Here it is 0.5, 0.5. We have 0.5 plus the mass of gas is this one, 24.94, minus the mass of the fuel. The mass of the fuel now, which is 0.94. The mass of the fuel, 0.9. The mass of the, there is the mass of the combustible fuel here, 0.94. Alright, then simply punch that, we'll find the mass of M. If we punch this, the mass of air there will be 24.5 kilojoules per kg of fuel. So this is what we have so far. So here next we'll have number 5. What do they want? Calculate the total mass of the flue gases. Total mass of the flue gases. Total mass of the flue gases must be equal to the mass of the air. Flue gases total mass of the combustible flue. Mass of the air is 24.5 as mass of this is 0.94, then this will be 25.44 kg per kg of fuel. All right. Number 6, what do we know? It says draw up a heat balance sheet in kilojoules per kg as per percentage to determine the uncounted heat uncounted. I've discussed about this in our introduction. Heat uncounted is when we minus everything from, okay, you can draw your component if you want. You can use the diagram. You can use this in the form of a diagram if you want to understand. If you understand like that, you can use the form of the diagram if you understand it that manner. All right. All right, balance sheet. Here we have our components. What we have, obviously it's A. You can say here B. We have obvious the plant all. C, we include in the plants, we have the moisture. D, we have what, the dry flue gas, the dry gas. It's our unaccounted, but I've discussed about this unaccounted. All right, so here supposed to have let's start by fuel supply. Okay, this is the components. Was fine. We'll have, let me just put here let me put here the fuel supply. All right. So let me write like this. All right, I can say let me erase this. I want to make it accurately. All right, here we can have our components, and here formula. Our heat, it's in kilojoules per kg, and our percentages there. It's our balance sheet. Component A, we have the fuel, right? The one that we can say we have the fuel supply or just fuel. We can say fuel supply or fuel. The B, we have N, maybe moisture, or okay, the plant. Here you can have the moisture, the heat from that. right, extend a little bit. So here we'll have D, which is we have the dry gas, E unaccounted, all right. So you know that to calculate the heat for to have the heat of this the heat of the to calculate the heat of the fuel, we know that it's a mass of the fuel multiplied by caloric value. So what is the mass of the fuel? The mass of the fuel we took it as per fuel, right? Multiplied by 3032, or it was in 32 times 10 to the power of 3, right? Multiply this by 32 times 10 to the power of 3. This will be what? 3000 0, right? Joules. This, right, is in joules. Then the heat of the plant will be, I've discussed that, will be mass of the steam over H4 minus H1, right? To calculate the mass of that, right, of the plant. It's always supposed to get the mass of the plant. So we can calculate that. The mass of the steam, we know that we have the mass of the steam. It was 8 into H4. H4, it was 3148 minus H1, whereby it's 188. We put that on our calculator. What is the value we'll get? 8 into 3148 minus 188, have 23,680, right? Then the heat of the moisture, it is given for us. This is given, and this was given. It was given, which is this of the moisture. It was 144.5. The heat of this, it was 6,000. All right, now the heat of unaccounted, you'll take the check. I've discussed about the unaccounted, guys. I said you take up the unaccounted will be equals to the mass of the fuel supply, the supply energy, the energy supply minus the total energy, total heat or energy, total heat in the system, Remember, this is what is mass multiplied by mass of the fuel multiplied by caloric value, then minus the other heats. Remember, minus this, subtract this, you sum up this, you add this and that, then no, you don't include, you exclude the one of the, sorry, you exclude this one, you add this and that, then you subtract it here, the total, you add, you sum up them, you subtract. Actually, let me show you. This will be like you have 3 Remember, for the fuel is 300 0. You'll minus this, you sum up the other heat, you sum up this, you add that, you add this, you add that. Understand? So you add 6,000 plus, you add 144.5 plus 23680 2368. Then you'll find the unaccounted. If you punch this on a calculator, now unaccounted will be 874.5, right? Remember this in kg per kilojoules. So simply here you can say this is same as A, what we have there, minus B C D, A minus B C D, like that. There you'll have these to be 874.5. all right. Now the percentage of years for the fuel, will take it as what will be, it goes for the, it be 100%. We start by 100%. 3200 times 3200 multiply by, right, that would be 100%. Here we'll have 100%. How? Why we'll have 100% is because we're taking the heat, then we divide it by the heat of the supplied, by the supplied value. How do we came about 100? We are taking all of this heat there, the heat of the, is dig like this. We want to find the percentage of the fuel supply. Let's say fuel supply percentage. We want the percentage of that. Remember, you'll take the value of the heat, you'll take the value of the of this supply heat, whereby the value it was 30,000, right? Divide by the heat of the supplied fuel times 100. You'll find this to be 100%. All of them you divide by the heat of the what of the fuel supplied, you come to the plant. You can come, you see plant, they want the percentage there on the plant, will be the heat of the plant, Q of the plant, divided by Q of the supply, fuel supply. So multiply by 100. So this will be the heat of this of the plant. It is here. It is 2368 divided by the one of the fuel. It is 3200. Multiply this by 100. If you punch this, you'll get what? 74 degrees. You see? So here we'll have what? 74 degrees. Continue on and on. Now you come to the moisture, it's 1. On the moisture you have 1,445.5. You do like that. You divide by that, you multiply by 100. 144.445.5 divided by 32000 times 100. Punch that, we get this to be 4.5%. You see, 4.5%. All right, so on now we come to the dry is 6,000 divided by 3, 2000 times 100. Punch this, get that to be 18.75 degrees. Then you come to this 874.5 divided by 300, like that. 3200 times 100. Punch this, you get this in your percentage to be 2.75 degrees. So this is how we go about filling up our heat table there. So we have found everything now, guys. So this is how it goes. Oh guys, thank you for watching, and then if you find this helpful, may you kindly subscribe to my YouTube channel and become the family by subscribing to our YouTube channel. And then we thank you for watching, and we thank you a lot for watching, for engaging, and then feel free to comment, and feel free to share this video with your fellow classmates. All the best. Thank you for watching. Subscribe if you have not subscribed. All the best. See you on the next coming session, right?